Good morning, students. We have been discussing about this number system, how data can be represented in different forms, how it can be coded, how data can be coded in different forms, and how the conversion between the numbers, different representations can happen. Okay, and in this class we are going to take one particular number in one representation and try converting it into all the other different forms. Okay, so that you will understand the relationship between these numbers in different representations. To recollect what we have learned, the decimal number system is a base 10 number system having digits from 0 to 9. Deci means 10. Okay, so this includes the numbers from 0 to 9. The weightage of these positions can be represented as 10 power 0, as 10 power 0, the weightage of the digit at the least significant position. 10 because it is a decimal number, the base of decimal number is 10, and the digit at the first position 10 power 1, the weightage is 10 power 1, 10 power 2 and so on. Binary number system. Bi means 2. So in computer everything is represented in the form of zeros and ones. The reason for that is the storage unit inside the computers are electronic switches that can have only two states, either on or off. On represent 1. Okay, if the switch is on, it represents 1, and if it is off, the off switch is used to represent 0. This is the reason computers use binary number system. So binary number system is a base 2 number system that has digits 0 and 1. So the weightage can be represented as 2 power 0 for the least significant bit, and 2 power 1 for the bit at the first position, 2 power 2, 2 power 3, 2 power 4, and the bit at the fifth position, the weightage is 2 power 5. 2 because it's a binary number system, the base is 2. And the third one is octal number system. Octa means 8. We also use octagon to represent. Octagon is a polygon that has 8 sides. Okay, same way octal number system. Octal is a number that has base 8, and that includes the digits 0 to 7. 0, 1, 2, 3, 4, 5, 6 and 7. The weightage is represented as 8 power 0. It is octal that has base 8. So it is 8 power 0, 8 power 1, 8 power 2 and so on. And hexadecimal number system. Hexa means 6 and decimal means 10. So it is a combination of 6 and 10. Okay. So this includes the decimal 10 digits, right? 0 to 9. Decimal symbols 0 to 9. And the 6 alphabets A to F, where A is equal to decimal 10 and B is equal to 11 and so on till F. The weightage of each position is represented as 16 because it is hexadecimal that has 16 symbols, that is used to represent the 9 digits plus the 6 alphabets. Okay, totally 16. So it has the base 16, 16 power 0, 16 power 1, 16 power 2 and so on. This table shows the relationship among the different representations. Decimal has the numbers from 0 to 9, and binary has the numbers 0 and binary has the numbers 0 and 1, and octal has the numbers 0 to 7, and hexadecimal has the numbers 0 to 9 and alphabets A to F. If you see this table, decimal number 7 is represented as 111 in binary and 7 in octal and hexadecimal 7. So here we understand from this table that to represent 4 digits 0 to 3 Here we have a 1 1. So we understand that to represent 4 symbols or numbers, we need 2 binary bits, and to represent 7 numbers, we need 3 bits. To represent 16 numbers, we need 4 bits. 4 bits are needed to represent 15 numbers. Okay, so that is 2 power 2 bits. If we have 2 binary bits, that can be used to represent 4 symbols, 4 different symbols or characters, right? If we have 3 bits, 2 power 3, that can be used to, these 3 bits are used to represent 8, 0 to 7. Okay, so that is why octal numbers are represented using 3 binary bits. Okay, so 2 power 3 is 8 different combinations can be represented. And when we have hexadecimal, if we take, we have 16 different symbols, 9 digits and 6 alphabets. So we need 4 bits because 2 power, yes, 4 is 16. Okay, we need 4 different bits, 4 bits combinations, 4 bit combinations of binary to represent the 16 different symbols. So 2 power n denotes the total number of symbols that can be represented using n binary bits. Yeah, based on the 2 power n combinations of ones and zeros, a binary code that represent 10 decimal digits must have at least 4 bits. The code that is commonly used for decimal digits 0 to 9 is the BCD code, binary coded decimal, and it is abbreviated as BCD. To understand the relationship between the different representations, here let's take one number from each representation and convert it into the other forms. So first let's take a binary number 1 1 1 0 1 1 0 1 0 0, and now it's a binary number. It has to be converted to decimal, octal and hexadecimal. And first, to convert it to decimal, the procedure to convert it to decimal is take each digit from the binary, take each digit and multiply by an integer power of r. Multiply each digit by an integer power of r, where r is the base, that is 2 here, as it is a binary number. So let's take the most significant bit, that is 1 into 2 power, the position is 0, 1, 2, 3, 4, 5, 6, 7, 8. 2 power 8 plus 1 into 2 power 7 plus 0 plus 1 into 2 power 5 plus 1 into 2 power 4 plus 0 plus 1 into 2 power 2 plus 0 plus 0. So that is 2 power 8 is 256 plus 2 power 7 is 128 plus 2 power 5 is 32 and 2 power 4 is 16 plus 2 power 2 is 4. That is equal to 436 in decimal. So this is the decimal equivalent of the binary number 1101101100. Now let's move on to the next form. To convert to octal, the procedure is write the binary number 110 110 100. and what we do is, as 3 binary bits are needed to represent the octal digits, we split it into 3. Okay, 3 bits, and 100 is equivalent to octal 4, and 110 is 6, and 110 is again 6. So the octal equivalent of the given binary number is 664. Now the next form is to convert to hexadecimal. The same procedure we follow to convert to hexadecimal. We write the binary number as it is, 110100, but here we need 4 bits to represent hexadecimal, so we split it into 4 bits. So 0100, and the second part is 1011. Here we have a single digit, that means we have 3 leading zeros, and 0100 is equivalent to 4 in hexadecimal. 1011 is equivalent to decimal 12, that is in hexadecimal equivalent to B, and 0001 is 1. So the hexadecimal equivalent of the binary number is 1B4. So here we write the relationship as the binary number 110110 is equivalent to 436 in decimal, that is equivalent to 664 in octal, which is also equivalent to 1B4 in hexadecimal. Now let's take a decimal digit, decimal number. Let's take a decimal number 673. It's a decimal number. Now this decimal number has to be converted to binary, octal and hexadecimal. So to convert to binary, to convert this number to binary, the procedure is divide the integer part by r. Divide the integer part of the decimal number by r. So here we have 673. We divide it by, here r is 2, means the number to be converted. Okay, it has to be converted to binary. So r is 2 here. We divide 673 by 2, and it is 3 2s are 6, and 3 6 2s are 12, and the remainder is 1. We keep accumulating the reminders. Here it is 1, and then again divided by 2, 1, 13, 6 2s are 12, 8 2s are 16, and the remainder is 0. Again when we divide it by 2, 8 2s are 16, and 4, 0. Then again 4, 2, 0, 2, 1, 0, 1, 0, 1, 5 and 0, 2 and 1, 1, 0, 0, 1. Okay, so the reminders, we need to now write the reminders from the last reminder. So last reminder becomes the most significant bit of our resultant binary number. So it is 1, 0, 1, 0, 1, 0, 0, 0, 0, 1. This is our binary equivalent of the given decimal number 673 is 10 10 1000001. 10 10 1000001. Now let's convert it to the other forms. The next we need to let's convert it to octal. To convert it to octal, we write the binary equivalent. Right, the first digit is decimal to when we convert decimal to octal, okay, we follow the same procedure how we converted to binary, but we divide it by 8 instead of 2. So let's take the number 673 divide by 2, divide by 673 and divide it by 8. 8 8s are 16, 64, 8 8s are 64, and 4 8s are 32. The remainder is 1 here. Again we divide it by 8, 1 0 4. Then when we divide it by 8, 1, and the remainder is 2. Now it is 0 and 1. When we collect the remainder from the last remainder, so it is 1 2 4 1, the octal equivalent of 673. Whereas to find the hexadecimal equivalent, we divide the number by 16. Fours are 64, 2, 32, and the remainder is 1. Again when we divide it by 16, 2 16 are 32, and the remainder is 10, which is equivalent to, in hexadecimal, that is equivalent to A. And divided by 16, 0, the remainder 2. So the hexadecimal equivalent of 673 is it is 2A1. So we write the relationship as 673 in decimal is equivalent to 1010100001 in binary, which is equivalent to 1241 in octal, and that is also equivalent to 2A1 in hexadecimal. And now let's convert an octal number. Let's take an octal number. It's 426. Okay, and convert and try converting it to the other representations: binary, decimal, and hexadecimal. So first, to convert it to binary, to convert octal to binary, the procedure is simple. We write the octal numbers 4, 2, 6 and write the binary equivalent of the octal number. Okay, 6 is equivalent to 110 and 2 is 010 and the binary equivalent of 4 is 100, and so here the binary equivalent is 100010110. To convert it to hexadecimal, it is the same way. We write the digits 4, 2, 6 because it's octal, write the 3-bit equivalent of each number. 110 and 2 is 010, 4 is 100. Now the resultant number we want is a hexadecimal number. So what we do is, we need to split it into 4 bits, as binary 4 bits represent as 4 bits as in binary 4 bits are used to represent the hexadecimal numbers. So here 0001, and here we have a single digit, we put 3 leading zeros. So 0110 is equivalent to 6, and 0001 is 1, and 0001 again is equivalent to 1. So the hexadecimal equivalent of the octal 426 is 116. So now, given an octal number, we have converted it to binary, and then we have converted to hexadecimal. The other form to be converted is to binary. So to convert it to binary, now we need to convert it to decimal. Okay, so convert any number to decimal. To convert from other representations to decimal, the procedure is, take the digits for first digit, most significant digit, and multiply the digits by the integer power of r. Here r is 8, as it is octal number. So 4 into 8 power 0, 1, 2, 8 power 2 plus 2 into 8 power 1 plus 6 into 8 power 0. Correct? This is equivalent to 4 into 8 power 2 is 64 plus 16 plus 6, that is equal to 278. So this is the decimal equivalent of the octal 426. So how we write the relationship here? 426 in octal is equivalent to 1000 10110 in binary, that is equal to 116 in hexadecimal, which is equal to 278 in decimal. Now finally let's take a hexadecimal number. Okay, let's take a hexadecimal number AF63. Now to convert this to, we need to convert this to binary, decimal and octal. So to convert this first to binary, what we do is we take the digits separately, A, F, 6 and 3. Let's write the 4-bit binary equivalent of all these numbers. 3 is equivalent to 0011 and 6 is equivalent to 0110. F is the last hexadecimal number is 1111, and A is equivalent to 1010. Now write these numbers together. That forms the binary equivalent: 1010, 1111, 0110, 0011. Now to convert it to octal, we do the same thing. A, F, 6, 3. Let's write the 4-bit binary equivalent 0011, 0110, F is 1111 and A is 1010. Now as we need the resultant octal number and we use 3 binary bits to represent octal, we will divide it into 3 bits 011, 100, 101, 111, 010, 001 and 011 is equivalent to 3 in octal and 100 is equal to 4, 101 is equivalent to 5, 111 is 7, 010 is 2, 001 is 1. So the octal equivalent of the hexadecimal AF63 is 1, 2, 7, 5, 4, 3. This is the octal equivalent and the binary equivalent is this. Now the next form is decimal. Any number to be converted to decimal, we take the digits and multiply them by the integer power of r. Here r is 16. So a into 16 power 0, 1, 2, 3. 16 power 3 plus f into 16 power 2 plus 6 into 16 power 1 plus 3 into 16 power 0. That is a is equal to 10 in decimal. So 10 into 16 power 3. 4096. It is 4096 plus f is equal to 15 in decimal. So 15 into 16 power 2 is 256 plus 6 into 16 plus 3 into 1, which is 40960 plus it is 3840 plus 96. 6 into 16 is 96 plus 3, which is 44899. When we add up all these, we get 44899, which is the decimal equivalent of the given hexadecimal number. So we write the relationship as AF63 in hexadecimal is equivalent to 1010111011000011 in binary, that is equivalent to 127543 in octal and 44899 in decimal. So here are the binary coded octal numbers. The octal numbers 0 to 7 are represented in binary form as 000, 001 up to 111. And the next number, if you observe, the next number is not 8, it is 10. and we take the digits individually. 1 is in octal, the binary form of binary equivalent of 1 is 001, so we write 001 here, and 0, the second digit 0 is 000, so it takes this binary digit 000, and 1 it is 001 which is equivalent to decimal, in decimal, which is equivalent to 8 and 9. This is the binary coded hexadecimal numbers. Here we have the hexadecimal numbers 0 to F, and which is represented with the 4-bit binary equivalent 0002 to 111. And the next number, if we take, it is the next hexadecimal number is 10. The binary equivalent of 1 is 0001 and 0 is 0000. So we write 0001, and second is 0, the binary equivalent is 0000. So the first 16 digits are already coded. So we use these codes to further represent any hexadecimal number. The binary coded decimal does the same for decimal numbers 0 to 9. Okay, the numbers 0 to 9 is coded as 0000, 1 up to 10. The 9 binary code, the normal binary code we use is 1001. And the next number, if you see, if you observe this table here, 10 is the next number. The binary equivalent is this, the next pattern is the 1001, and the next pattern is 1010. Whereas the BCD equivalent of 10 is, we take the binary equivalent of 1 first, BCD equivalent of 1, which is 001, and for 0 it is 0000. So that is the binary equivalent of 10, 0001 and 0000, whereas the binary equivalent is different. Many applications of digital computers require handling of data of different form, right? Not only of numbers, that also consists of letters of the alphabets, and special characters. So this alphanumeric character, if you take an alphanumeric character set, okay, it includes the decimal digit 0 to 9 and the alphabets A to Z and capital and small letters of alphabets, and then some special characters, okay, which are commonly used to represent data. So here we have this ASCII ASCII format. Okay, ASCII is American Standard Code for Information Interchange. Okay, ASCII is expanded as American Standard Code for Information Interchange. This ASCII is used to represent the alphanumeric character set. Okay, the data that consists of alphabets, numbers, and all special characters. Okay, we need some code for representing that data, because data does not only contain numbers. So we use ASCII code here. Okay, this is the ASCII table I have given for your reference here. These are all the ASCII characters. Okay, null, the first character null, and start of heading, start of the text. These all need to be coded for the computer. Okay, so for these characters, these are ASCII characters. At the decimal equivalent, you can see 0 in decimal. Okay, here it is equivalent to this character. Binary, octal, and hexadecimal equivalent are given. Okay, it is American Standard Code for Information Interchange that uses 7 bits. Okay, a 7-bit code. So as it is 7-bit code, 2 power 7, which is equal to 128. Okay, totally 128 characters can be represented. If you observe this code, here initially we have all the special characters. Okay, and then here character, 0, where I'm pointing here 0, it is the decimal equivalent is 48. Okay, 0 to 9, digit 9, and then again we have some special characters in between, and then A, capital A is okay, equivalent to, it is in decimal, it is 65. And then it is coded as binary. You can see the binary code of this. Okay, this is the equivalent binary code. Capital B, etc. up to capital Z. Then again, small alphabet A is equivalent to 97. Okay, so this is ASCII code. Now you can try converting your name. If your name with some space in between, if you have two names, first name and second name, separating them by space, and if there is a period, if there is a dot, okay, this is the, here we have dot, okay. So how we write, how you represent it in binary or in decimal, okay, ASCII equivalent you can write. Okay. And here are some exercises to do. The first question, convert these decimal numbers to binary. And here convert these decimal numbers to the indicated bases, octal, hexadecimal and binary. Then here third question, convert the hexadecimal number F3A7C2 to binary and octal. And for this fourth one, you need to make a table of a 12-bit register and write the binary coded octal, binary coded hexadecimal, the 4-bit equivalent, and binary coded decimal BCD for the decimal number 215. And here the fifth question, decode the ASCII code which is represented by binary. Thank you.